Okay, we are now live. Hey everybody, and welcome to your first Q&A for Neuromatch Academy. So I'm Megan Peters. I hope your first day went great. I think you just watched my outro video. And so here with me today are three other excellent computational neuroscientists. So I'll let them introduce themselves, then we're going to do some discussion, we're going to do some reflections. It's going to be awesome. And then we'll also do a little introduction to how to use Crowdcast after we do that. So why don't we go ahead and go first? Jeff, you want to go first? Introduce yourself?
Sure. My name is Jeff Erlich. I'm an assistant professor at NYU Shanghai. I'm in Shanghai, China right now at 2 p.m. My lab works on mouse, rat, human, and synthetic subjects. And I would say that most of our modeling is at the cognitive behavioral level, but we also do some attractor network type dynamical systems modeling. But I would say I sort of almost consider myself like a cognitive scientist these days, just thinking about like the algorithms of behavior rather than the details of how the neurons are doing it.
Cool, thanks. And Arvind, you want to go next?
Yeah, sure. Hi, my name is Arvind Kumar. I'm based in Stockholm at the Royal Institute of Technology. I'm a computational neuroscientist, and I have remained computational neuroscientist since my PhD days. Before that, I studied electrical engineering, and then I don't know how I managed to get into neuroscience, but this is so much fun. When I switched, neurons pretty much looked like electrical devices, and that was my entry here. And I have stayed with that idea still. I think there is so much to learn about properties of neurons, not as individuals, but as part of networks. So that's what I've been doing for the last 15 years or so, trying to understand the properties that the neurons' connectivity renders to the networks. So I'm really at the hardware level and trying to understand what it means to connect neurons, and then some function emerges in that network.
Awesome, thank you. And Ulrik, you're next.
Right, so my name is Ulrik Beierholm. I am an assistant professor at Durham University in the north of England. And I am in the psychology department, and I work mostly with humans. I do modeling, computational modeling, of course, of different types of behavior, most of the cognitive type of stuff. And we use, partly behavioral stuff, partly EEG, partly fMRI, basically whatever kind of fun tools we can get our hands on, and try to model partly perception, partly reinforcement learning, part of decision making too.
Cool, thanks.
And I'm sitting in my garage right now, as you can tell.
You're what? Sorry?
I'm sitting in my garage right now, as you can tell.
Your home office, right? Yeah. Cool. So, and everybody, I think, probably knows who I am now, but my name is Megan Peters, in case you guys missed it. And I'm an assistant professor of cognitive sciences at UC Irvine. So there was a bit about that in the welcome video, but maybe that was a long time ago by now. You guys, your brains are probably very full. And so just to remind you, I work on human neuroscience with fMRI, EEG, and computational modeling. So what we're going to do now is we're going to do a little bit of discussion. So at the end of the video that you guys all watched, we talked about the modeling goals and how there was this massive diversity of goals in different models, and how all goals are good and valid and just are different from each other. And so what I'd like to do now is we're going to put one of those slides back up on the screen, and we're going to do a little poll so you guys can vote on which of these 12 goals you think are the most important. And you have to just pick one, okay? Just one. I know that's kind of not fair, but let's just pick one. So I'm going to have to kick one of you guys off screen here. Who should I kick off? Sorry, Arvind, I'm going to kick you off. And so now I'm going to share my screen. And I'm going to allow this window here. Can you guys see this? I think you can see it.
Not yet.
No. Okay. Well, I didn't check my stuff before, so I guess that would be different. Oh, well. Let's just put the poll up, and we'll do it this way. So let's put the poll up. So you guys should be able to see the poll now, I think. No?
Well, I can't. Maybe the other people can.
Can you guys see a poll? Can anybody?
Oh, there's a poll link at the bottom.
Yeah. So if you go to the polls at the bottom.
Oh, yeah. I see it.
Here,
you can like click
and
it.
you guys can click on that, and you can pick which one you think is the most useful. Okay. And so you can actually watch in real time which of these goals you think is the best one. So sorry, I don't have any slides for you guys. While you guys are doing this, let's see if I can fix that.
What's the goal of modeling?
Yeah.
By having real-time feedback, it can bias future voters. They're like, oh, do I want to be part of the crowd or do I want to be different?
That's true. That's true. So try not to look at, what other people. A lot of people like useful models. I suppose that's useful, but also interpretable. Interpretable seems to be very popular. Okay, interesting. How about you guys? Do you guys think that any of the which one do you think is the best one?
I think a normative wasn't getting enough love right now, so I
All right, I'll switch mine to normative too. You can't switch.
Okay.
I mean, useful is very broad.
Useful is very broad. Yeah. Useful is good at solving real world problems, right? Like we're not really sure what those problems
means.
Huh?
Is that what useful means? Real world?
Well, these are the things that we put up in the slides, right? Like good at solving real world problems. Like maybe there's a real problem to potentially solve.
Oh, I see.
Okay.
Inspiring experiments is obviously something that's really important too, right?
Yeah, I think
it's nice when a model can describe all the previous data, but if it actually gives some ideas of something new we can do, some new experiments, then that's awesome.
Yeah, I think that's really important too. That's one of my favorite things to do with models, actually, is you kind of say, okay, I've got this model and it has behavioral realism and that's wonderful. But then if I push on the model in this particular way and I break it, then I can design an experiment and try to break the human in the same way or break the brain in the same way. And I think that that's really fun because then if your human and your model break in the same way, then maybe you got something right.
Yeah.
So that's pretty cool. All right, cool.
Breaking brains is pretty fun.
Yeah. Okay. Well, I'm going to bring Arvind back on the screen here because apparently I didn't get my screen sharing working right. So that's too bad, but we'll have to make do. So Arvind, welcome back. He's connecting now.
So interpretable one.
Interpretable one, huh?
34 votes.
It did win. Okay. I wonder. So if you guys have any questions about that also, like in Crowdcast, you can click the Ask a Question button at the bottom. And that Ask a Question button will allow you to actually ask specific questions, then other people can upvote them. So people can vote on what is the kind of most important one. Okay. So the thing that I'd like to do first before we do that, and I really apologize for the screen sharing not working, guys. So I'm going to just have to talk you through it and you will have to bear with me. But I hope that everybody is in NeuroStars. Have you guys hooked into NeuroStars? Everything is working there. You can respond in the chat and let me know. Is NeuroStars good? Yes, no, kind of, maybe. Maybe. Come on, guys, in the chat. So if NeuroStars is working okay, sweet. Okay, so if NeuroStars is working okay, at the top of your NeuroStars categories, there are these links for surveys, and you should see this whether you're either an observer student or an interactive student. So there's these surveys we're calling them reflections, okay? And so the reflections, the idea here is that we want you to take a moment to kind of think about what we did today, and we know it was super fast. We know that it was super intense. and that you had like a nice break in the middle where you maybe got a chance to eat some food, and then you came back and did more intense stuff. And so these reflections, the idea is to think about, what did you know when you came in to today? What did you have a background in? And then what did you leave with? You know, did your thinking change? Did your ability to apply these ideas in your own research change? And so if you guys can go into NeuroStars, and again, I'm sorry I can't share my screen, but if you can go into NeuroStars and you can find at the top of NeuroStars, in the interactive students or the observer students category, you have a little drop-down menu. And then you'll have a daily student reflection link and information. And if you can go in there and you can click on the link that goes with your pod, essentially. So you drop down in the survey, your pod, and you tell us what you think. And there's another thing that's really important about these surveys that we want to tell you about too, which is that this helps us figure out if your pod is working well together, if you have good communication, if you're able to find everything that you need, all of that good stuff. So if you want to take a moment now and just click around in NeuroStars, and if you're lost, please let me know. Let's see if we've got some questions about this. Does not look like they're all about the tutorial so far, so that's good. Nobody's lost. Fantastic. And we'll get to these questions in a second. But if you want to take just a couple minutes now while we're kind of chit-chatting about these goals, to think about what you did today, to think about what you came in with and what you left with. And then I can also post the links in the chat. I suppose I can do that. That would be fine. And so I will do that right now, and that will help. So here is the link for the interactive students, okay? I'm putting this here. This is for the interactive students. And then this is for the observer students, okay? So if we've got some observer students here, you're also encouraged to do this. We know you don't have a pod, but that's okay. We're still really interested in what you guys are thinking about this. And so this helps us make NeuroMatch Academy better for the future and so on. So here's all the links in the chat. You guys can go and do that. And while you guys are doing that, we can continue talking, maybe take some of these questions that you guys have done. So so we've got
Can we see the questions? Or
I think you guys can see the questions too. Yeah.
There's a
So
link
in the
at the
ask
bottom.
a question at the bottom, and people have
there's a separate tab.
Yeah.
I see. Okay.
So we've got some questions about the tutorials, and we can try to do some of those, but we also want to do some big kind of overview questions. And so if you do have specific questions about your tutorials, a great thing to do is to actually ask your TA, because I bet you there are a bunch of other people in your pod who have a very similar question, and then you guys can have a really great discussion about it. So here's a question at the top. As we were looking at the neurons one by one, there are many neurons behaved exponentially distribution-like, but there are also that kind of do something different, right? Neurons that kind of behave more uniform distribution-like, meaning their spike counts are a little bit more uniform. So what are the possible mechanisms for this? And we've got some nice answers, some nice comments about this, but do you guys want to do any of this? Anybody have some ideas?
I mean, I've never seen a neuron with a uniform ISI distribution.
Yeah.
So I'm a bit confused.
So yeah, it's about like whether it's a spike rate or whether it's an ISI, right? And so this would be, I think this is for ISI, like the mechanisms. I do feel like it would be very difficult to have a ISI distribution that would be kind of uniform.
Right. You could have something a little more flat, gamma or Gaussian. So like anything that's like a pacemaker will look Gaussian, basically. Like it'll have a peak with some noise. And the information content there is pretty low. It's just like a clock ticking.
Yeah. Okay. So let's do that one. The second one is kind of very similar. I think. And so I think that let's go to the third question here, which is like the match. This is kind of a broad overview question about like the what, the how, and the why models, right? How to reconcile the models. How do we reconcile the models between, especially tutorials 2 and 3, the how model and the what model and the why model? So this question comes from Yi Yan. Maybe you want to come up on screen and do a little more, or would you rather just stay in the chat? We can do it either way. I can actually call people on screen if you guys are feeling brave. So if you're up for it, we can do that as well. So Yi Yan, if you're here and you want to be on screen, just say so in the chat and I can call you up. So I think it's kind of interesting to think about, like, how to make the models consistent with each other. I kind of think you don't need to make them consistent. I think that a single model can do kind of multiple heavy lifting. What do you guys think?
So sorry, I haven't seen the tutorial. Do you mind explaining a little bit more what, why, how, and what?
Yeah, sure. So I had these cute hats. Oh, maybe I still even have my hats. And Conrad had some cute hats too in the tutorials. But the idea is that the type of model that you're building depends on the type of question that you're asking, right? And so you can have a descriptive model, which is you want to find the best description for the behavior, but you don't really care about how it works or why it does it that way. And how model then would be more like a leaky integrated fire or a Hodgkin-Huxley kind of approach, where you're saying, okay, what are the mechanistic reasons why the system behaves in the way that we've described it? And then the why model is, why did the system evolve this way? So this is kind of a normative question. So they kind of map onto Mars 3 levels, right?
Yeah, it sounds like it.
A little bit, except for the descriptive level model doesn't really quite fit in the thing, in the hierarchy. So I think they don't need to necessarily be consistent with each other. They don't necessarily need to be separate either.
But I mean, if you want a full understanding, you need to like have maps from the concepts in one level to the concepts in the other level, right?
Yeah.
And I think this is actually like one of the biggest challenges sometimes when like neuroscientists talk to the public or to psychologists. Like when we say memory, maybe we mean like persistent activity. But when a psychologist says memory, they're talking about like the experience of remember, like, you know, there's this, we use the same word, but there's actually like a pretty big conceptual gap sometimes between the meanings. I think it's a real, I mean, I consider this one of the great challenges of any science, is like how you bridge conceptual levels. Like how do we, you know, that's, it's a real challenge. I don't know what that's not helpful.
But I think I'm with Megan on it. There's no reason why they should be reconciled, because every model you construct to answer some questions. It depends on your questions, which level you want to explain, whether you are happy with a why model or a what model or how model. Sometimes, if you just let me indulge a little, I think it goes very way far to Aristotle, who's thought about like what is explanation, right? And he talks about different kind of explanation, like whether it is an efficient cause, whether it's a causal explanation, it's a material cause, it's a formal explanation. So he talks about these different levels. Some of them are like, when we talk about a mechanistic explanation, then we really want the model to answer questions related to the hardware of the brain. And this is useful when you are thinking of clinical explanations. So in that sense, it makes a lot of, it's pretty good to have a Hodgkin-Huxley model, right? If you want to control the neuron spiking behavior. A leak integrate fire neuron would not help in that. But if you're only interested in, you know, that, yeah, there is a spike occurring, or I'm only interested in ISI interval distribution, then leak integrate fire neuron is perfectly fine. You can talk about why it should be, right? That's the formal cause in Aristotle's sense. I don't think there is a good answer for it. For formal cause, we always come up with our own expectation.
I definitely think it all comes down to the question, right? And this is something exactly. that goes through both, like whether you're doing experiments or whether you're actually doing modeling, right? It's about the question, and something that, you know, we have to tell students over and over again, of course, you know, what's the real question that you care about, you know, and that really should be framing your entire thinking, whether it's modeling or experiments that you're doing.
Sometimes your question, though, it ends up falling into multiple categories, right? Or the model that you build falls into multiple categories. And so maybe that's like this kind of consistency idea, is that you come up with a model that can bridge the gap a little bit. And this is why I think we should not try to force models into this like what, how, why. And that's why we also talk about, Mars 3 levels of analysis as another way of possibly categorizing models. And then we also think about like levels of abstraction, which is like, neurons all the way through people. That's another kind of way. You can have mechanisms in people and you can have mechanisms in neurons. So maybe that's kind of how we should think about this a little bit.
Can I ask Arvind a question, actually? So if I'm, let's say, like a pharmacologist and I'm trying to come up with a drug that like cures epilepsy, let's say, like, is that kind of goal? So for a model that like predicts whether a drug is going to work is a useful model for that. But does that really apply to Mars? Is this something that I feel like Mars levels is more about like gaining explanation or gaining understanding, not so much solving like an engineering problem? Because he's talking about the goal of the system rather than like the goal of the scientist, right?
Yeah, but I think we can hack Mars' approach a little bit in this because if you now define epilepsy as somehow instability of the system, right? So that's then becomes the
goal is stability.
If stability is the problem, right? So I don't know what stability is needed for, but that will be somewhere a requirement at the algorithmic level that the system should be stable. And then you can go down at the implementation level that how is this stability being implemented, and there comes out your drug then. So I think this is how you could hack a Mars way of thinking for this.
Yeah, it's a great answer.
I like that, though, because it kind of shows that you can have a set of goals. You don't have to have just one. I know it was kind of like fake that we were like, oh, pick just one that's like the most important in the poll, but you can have this set of goals. That you have a train of goals with this kind of cycle. And I think this is part of what's going to be talked about tomorrow in the modeling process too, which is like there's this cycle of like, okay, once you've done the testing and the publication, now what? Now you go back to the beginning. And so then you ask a different question maybe about the same system. Cool. Okay, what other questions? You guys got any questions in here that you particularly want to answer? Because you guys can see these too, right?
Scrolling through.
Yeah. So, here's one that I like. What is the main purpose of computing entropy when comparing models? So this is actually a really good question. The main purpose is to see whether entropy ends up, this is one of the main purposes, is to see whether entropy ends up being able to differentiate between models. Because if it does, and one of them maximizes entropy, then you know that this is kind of a normative model. This is the best mathematically that a particular model could do, or that the system could do by this metric. And so we use entropy to compute the information in the system, but you could come up with a different metric too and see whether the model that's the best under one metric ends up being the best in another metric. And so one of the things that we'll talk about over the next couple of weeks is model comparisons, model fitting and model comparisons, and how if you want to pick like the best model, then best is all relative, right? Best relative to what? You have to like decide on your loss function. You have to decide on what loss function the system is using. I know that everybody here fits models and has done comparisons across loss functions and those types of things. Ulrik, I know you've got some papers about that.
I've literally spent years doing those kind of things.
Yeah.
I want to add one more thing here, because in this question, there's one line which says, do you mean if ISIs become bigger, the exponential will not be the best solution? I don't think this is correct, because in a way, and you want to use this class of models like maximum entropy model, their exponential pops out because you are fixing a firing rate, meaning you are saying that my mean interval is this much. And then if you don't assume anything else, then the exponential distribution turns out to be the with the highest entropy. So ISI being big or small has nothing to do with the shape of the distribution.
Awesome. Thanks.
Although you do run up against the refractory period at some point.
Oh, great point, Jeff. Yes. I mean, clearly, this idea that neurons are Poisson or renewal, that doesn't hold, right? So you will end up with some kind of correlations in the time domain. Absolutely. I think we forget this when we go onto the Poisson track and exponential distributions, that we forget that neurons have refractoriness. Yeah.
Awesome. Okay, well, we can make our way through these. These questions are great, guys. Keep them coming.
There's a question about like, how do you know that your neuron that your spike comes from? Oh, it seems like I got cut off for a second.
Oh,
Can you still hear me?
I hear you. Yeah.
Okay. Let me see if I can recover this.
Technology.
So the question is about like, how do you know a spike comes from a single unit versus like a single neuron versus not?
And like neuropixels.
Or in any spike recording system.
Yeah.
And I think the answer is it's a real tough problem. Like it's relatively unsolved. The spike sorting problem is a continuously challenging problem. There's very few data sets that give us ground truth because you have to do like an intracellular recording at the same time as a extracellular recording. And so we do our best, but I don't know if there's a universally agreed upon kind of solution.
Yeah, I don't do spike sorting myself. I work with some people who do, but I think you're right that this is a really hard problem, and generally the kind of logic is if you see two spikes too soon, too close together, then they're probably not the same neuron spiking twice really super fast. And so this is like because of the refractory period, right? And so then you think, okay, well maybe this electrode is listening to two different neurons. And so this is in response to this question by Yan Ming, who is asking, how do we tell whether it's a single unit or a multi-unit, and also like what's the difference between a unit and a neuron? Here, it's kind of they're usually used interchangeably in this kind of context, but you still have to figure out whether the spikes that you're seeing are coming from like one unit or several. And that's a hard problem. And there's a lot of people working on it.
There was a nice paper though saying that not all analyses are particularly sensitive to the answer to that question. So I think from Krishna Shenoy and some of his friends, maybe Mark, there's like a neuron paper basically doing population analysis, not worrying about spike sorting at all. And depending on your analysis, you get a lot of pretty much the same answer. That's
great. That means that your question and the way that you're going about it is kind of robust to the assumptions of your analytic pipeline, which is not always the case.
Robustness is actually something we really, as modelers, need to care a lot about, right? Like, we need to make sure that our models are not super sensitive to small details in parameters, for example. So that's an important issue.
But this discussion about spike sorting and whether unsorted spike trains are also useful, I think this also has something to discuss here, that from an experimentalist perspective, treating a multi-unit spike train is totally fine because your goal that time is to link some behavior to neural activity. Now, this becomes a great modeling challenge now if you treat that multi-unit activity as a single unit activity, or you treat it as a multi-unit activity, meaning many neurons are contributing. So building the mechanistic models becomes distribution gives you a more centered distribution. What you need to understand is that how a neuron spikes in this case. In leaky integrated fire neuron, it sums up inputs and then it hits a threshold. If you only excite the neuron, then your in-membrane potential goes above the threshold, and then it just keeps spiking because there is nothing else it can do. So this we refer to something as the mean-driven stage, where the mean membrane potential is above the spike threshold. That every time, basically the drive is so strong that neuron has nothing else to do than spike, and it will just spike with respect to the membrane. But if you add inhibition does two things. One, it reduces the mean of the membrane potential because excitation and inhibition are negative. However, when you add these two, your fluctuations become very low. So what happens when you add?
Hello. Okay.
Australia and Canada are also central.
I'm really? I can hear you, but it is kind of coming in and out. How about Megan? Weird. Oh, so I can just monologue for a while. What were we talking about? I was busy trying to solve my webcam problem. Okay. Sure. How do we know that our model is correct? All models are wrong. Someone already wrote that. All models are wrong. Yeah, so that's a great question. It's a great question. Oh, the model is right, but reality is wrong. I follow Andrew Gelman, who's a statistician at Columbia, who's one of the authors of the STAN modeling program, and I think he has a lot of good advice on these types of questions. He has a great blog, Andrew Gelman. Andrew Gelman. There's a lot of funny. Oh, look, he has the book right there. Bayesian data analysis. I'm getting a lot of like thumbs up in the chat, like, hey Jeff, just keep going. So right, I mean, so when I was an experimentalist during my PhD for the most part, and during that time, I saw the main point of models is that it forces you to quantify your hypotheses. There's a lot of, if you don't have a model, then you're just using words, and words are easily misinterpreted. But if you have a model, it's very clear. You have quantitative predictions. It forces you to be careful. And then I joined Carlos Brody's lab as a postdoc, who's a pretty well-known computational neuroscientist. And we were reading papers on attractor dynamics. And I just felt like all of these toy models where it's like a two-dimensional, like we know the brain is not a two-dimensional attractor, because that would be pretty boring. So what do we really gain when we say like there's like we say it's biophysical, but it's so simplified that it's like very abstracted from what's real. And I struggled with like, how do we know when we're like really learning something from our modeling and when we're not? I guess people are going to try to reconnect while I keep going. I'm somehow the only. No, apparently you're not even live. It's just like only me.
I tried to read.
Oh yeah, so people are asking for it's Andrew Gelman is I think he's got a blog. I think. Okay, so Conrad's just saying like keep going. Okay. Oh, Arvind's back. Great.
I tried to reload because that's what Conrad said.
Okay. So Megan, if you reload, we're all gone. We're all goners. Megan cannot reload. What you can do is join on your phone or something. No, then just mute your other thing. Yeah. Okay, so let's see what other questions do we have. Right. So there's another question actually, which actually I think is a really important question, which is when we don't know the ground truth, how do we know if our model is good? And there's actually a good answer to that, which is always generate synthetic data. So whatever you're trying to model, always make data that you know what the true parameters are, and then generate a data set which has all the properties that your actual data set has, but where you know the truth, and then fit your model and make sure that you can recover the true parameters. If you don't do that, I'm probably not going to believe your results. I hope I haven't offended anyone. Okay. So Arvind, do you want to pick another one?
Yeah, I'm just looking through it. Have you noticed something interesting that I could take?
There's a lot of questions about like ISI, and there's a question about the relationship between entropy and information. Why do we use Poisson distribution? Oh, that's super good. I'm wondering whether computational neuroscientists suffer a lot during the time in which your model does not match the experimental data at all for a long time. How do you get through it? Yeah.
Okay, I think so. I can say something about it. I don't know if it's a good answer, but we can take this up. Obviously, it's a good news when your models are not fitting the data. So that means that you need to revise your thinking, and you need to define better models that will match with the data. So that definitely it's definitely not a bad thing that your models are not fitting the data. Now, what do you do in that case? You can always fall back to the normative side, that you try to refine your models. You try to come up with better arguments, because if data is not fitting to models, there are two problems: that your models are wrong, but also it's possible that the data is wrong. We are measuring something that is not useful. this continuous interaction between modeling and data. It's not a one-way process that you get the data and you model it. Your model should also guide the data collection. So I think this interactive loop should be activated more and more rigorously and vigorously when there is a mismatch.
Yeah. But I think that in general, scientists are kind of long-suffering. Like, if you don't have a lot of patience and a lot of determination, I think it's pretty hard to be a scientist, because we work really hard to make really tiny baby steps.
Yeah, absolutely. I mean, it's a long-term commitment, right? So
it's a long-term commitment. Ulrik's back.
I'm back too.
Can people hear Ulrik?
Hello.
Okay, great. Yeah. Right.
Ulrik is also quite silent.
That's my natural disposition.
Ulrik, you want to take up some questions? Because
Let's see if there's anything not specific to distributions of spikes.
There's a question that's sort of philosophical about why do neurons have a refractory period? It's not philosophical. I think that's just a limitation of biology, right?
Yeah.
I would also say that it's the materials that we have been given to make a neuron.
Yeah.
Yeah.
There is a question about, like, what, presumably the actual value of the refractory period is subject to some evolutionary pressure. That there is some pressure to get it down to like 1 to 2 milliseconds, but faster than that, like the energy versus speed trade-off is not worth it or something. That's a hypothesis anyway.
So there's a fun question here about, is there a Y model that can explain the existence of the refractory period? So I'm gonna modify that a little bit and say, you know, is there kind of a normative explanation for why you'd actually want to have a refractory period? And I don't know if anyone's actually looked at that. I totally agree that, you know, refractory period is just a limitation of the actual material that you're working with, right? You know, that depending on what material you will have a different refractory period. But, you know, if anyone could come up with the good reasons for why it would actually be useful to have a refractory period, you know, that seems interesting, but I don't think anyone's actually looked into that.
Right.
But maybe refractory period doesn't have an explanation, but people do come up with explanations that why neurons have such extremely low firing rates in most part of the brain.
Yeah, no, that's good.
The argument is always about energy, right?
Yep. Firing
So
actually.
do you guys believe that argument?
At a large population level, you could tag them together.
Do you guys believe the energy argument about spikes?
I don't.
What do you think is the constraint?
I mean, energy, of course, is a constraint, right? Of course, we can't heat up the brain so much that it just burns itself.
Right.
But I think having a powerful brain gives the organism much more advantage to harvest energy, that it can always compensate for that. To me, for the brain to be optimized, I think the better constraint is that it should reduce the variability in the output of the brain. It should be more and more precise. Right? If I'm a monkey trying to jump from one tree branch to another, I do want to catch it because there are fruits there. It doesn't matter how much energy it takes. If I miss it, I'm done. But if I'm reliably doing it, even if it takes energy, I'm getting enough glucose.
Right. I mean, I think it depends a lot on your ecological niche, right? Like, if you're a koala and you have no predators and all you do is like sit in a tree and chew on eucalyptus leaves, you don't have a lot of pressure to be fast or precise.
Oh yeah, fair enough. Then you have even that constraint is gone. Absolutely. Then you need humans to preserve you.
Now you do. Well, humans first to take away your, like,
Yeah.
and then other humans to push back.
But if we follow that argument, then there should be different ecological pressures for different animals towards have different trade-offs between position and, metabolic, restraints, right? So, that's an actual empirical question you can then go out and look at. You can look at the firing rate of neurons in koalas versus firing rates of, I don't know, rats or, whatever. I don't know what the right animal is to compare to, but yeah.
It's a great. Has anyone done neurophysiology in a koala?
Don't know.
They're too cute. They're too cute. You can't do it.
We don't like doing experiments on cute animals. That's true.
We do not.
But I mean, number of animals in neuroscience are decreasing, so that's also important.
Yeah, true.
That's unfortunate.
All right. What other questions do we want to answer, guys? We're almost out of time. I can't believe it.
It's so much fun.
Yeah, this is fun.
I mean, just to go on this energy thing a little bit, like one of the things that I think is really missing from a lot of computational modeling, but also artificial intelligence work, is the energy constraint. Like brains formed with these constraints, like heat, energy, maybe speed, all these resource constraints. But usually when we model like networks of neurons, we don't think about the energy costs at all. We usually just assume that like there's enough energy and we don't have to worry about heat dissipation and we don't have to worry about building up of metabolites. And I just wonder like how much adding that stuff in can really help us think about cognition. What do you guys think?
I mean, there are areas where that is being taken into account, definitely, in certain amounts of like reinforcement learning, for example, it's a key constraint too, right? So that, I agree, it's something that we can probably think of in more different types of diverse models. But there are, of course, areas where it is being taken into account, definitely.
So you mentioned RL. Can you flesh that out? Like, you mean this whole like the cost of planning kind of thing? Yeah, I mean,
there's one of the interesting things about RL, of course, is that you can put in to your reward functions whatever you need, right? So, if planning, for example, is something that's important, then you need to put that into it too. If just movement, for example, is important, you need to put that into it too. You can load into your reward function whatever you think is the most relevant, and then you can go out and compare that to the behavior of an animal, for example.
That's true.
Can I pick on something you said? Which is that you can load into the agent whatever you think is most relevant, but then you are playing God, right? Like, shouldn't we kind of let the system figure it out on its own? Like, isn't this part of the I don't know, exploratory process?
Yeah, no, okay. So whenever we're modeling, of course,
then you put it in as a free parameter and you estimate how much the movements cost.
That's the thing. You can do meta learning too, right? And there's a lot of work being done right now on that too. Yeah. So that meta level where you actually have to learn the reward functions too. And there's some really cool stuff, of course, being done, especially related to kind of more AI side of things. Yeah. That really is kind of pushing those kind of ideas right now. So that's kind of one of the really interesting areas actually.
Yeah, I agree. I think meta learning is really, and I think, I don't know if we're going to get into meta learning by the deep learning ends of the course. We might touch on it a little bit. I don't think we're doing meta learning, but yeah, I agree that that's one of the more interesting things. Like if we just play God and we like implement the cost function that we think is the right one, then odds are we probably got something wrong. And so we should let the system kind of discover it on its own.
As modelers, we always make choices, right? We always have to make decisions about what do we actually think we want to learn. But it's really exciting if we actually find ways of letting the system learn about these things too, which is really what meta learning is about.
Yeah. So if you guys haven't heard of meta learning, all you guys out there, you can go check it out. There's a lot of, it's like a really hot topic right now. And I know hot topics are not like always the best ones, but it is kind of an interesting way to go. Think about letting the system teach you. Yeah.
I mean, the meta part is a bit funny. It's more just like we decided reinforcement learning was one little thing, and then everything that's beyond that is meta.
There are all these different implementations of meta learning now, where it's like, oh, we have to then make choices about, is it the derivative of the weight update rule that is the thing that is the actual like needs to go into the cost function, and then we get into the second level of like making decisions and playing God.
Yeah.
Oh, good. We've got some questions in the chat of what is meta learning. Oh, fun. Go look it up. It's like this whole branch of machine learning that's really hot right now. And so if you want to go take a deep dive into a lot of math, you might discover something really interesting. Yeah. I think one, you guys didn't answer this question, right? What do any of the models among like the how, what, why, and also maybe like Mars 3 levels answer the question of what the brain is actually doing? It's kind of a philosophical question. It can be a very concrete question, but it can also be kind of a philosophical question. It kind of leads from what we've been talking about, I think.
Megan, are they familiar with Mars level? Because I don't know if they
went over it very briefly today. Yeah, in the outro. Yeah, so in the outro we have, or they did like the what, how, why in the tutorials, and then we start to link them to Mars 3 levels. And so as a reminder, because I know it's fast, but we've got the computational, the algorithmic, and the implementation level, and they sometimes map onto the what, how, why, but sometimes not. And so do these Mars levels of analysis or the what, how, why, do they answer the question of what the brain is actually doing? There's a very like concrete way of answering this question, and it's also a very like philosophical kind of heady question.
There's one question which I think one of you should take. I don't think I can say anything useful there. This was it's hanging for some time now. It says why we can use 5 to 15 intervals as representative sample based on the, let's say, interval time / total time equal to spikes in interval / total spikes in tutorial 1. If we need to do tests, the deviation or other statistical characteristics, but I think the question is about finite data.
Yeah, I mean, it's a good question. I think for the sake of the tutorial, it was just like a very basic check. It's more like if the % of spikes in that window were very far off the overall duration, you would say it's definitely not representative. Like if the first 1% of the time contains 50% of the spikes, you would say this is not representative. But if it does match in percentage, it doesn't mean that it is representative. So how would you check? Probably KL divergence, I guess, on the ISIs or something, which is a statistical test of whether two distributions are the same. So you can look at the distribution, the first 5 to 15, 15 to 25, whatever. 5 to next 10 seconds, next 10 seconds. See if they're similar. Should we go back to the philosophy though of like,
like, are we actually learning anything about brains? That might be a good place to kind of wrap it up a little bit, because we're coming up on the hour here. We can end with a little philosophy. Everybody should study a little philosophy. That's my plug, by the way. Everybody should study a little philosophy. It makes you a better scientist.
I agree.
And always ask a question like this, which is like, are we actually studying the thing that we think that we're studying? Which is why I said like
the whole point of the NMA is to teach the kids how to like ask a question.
Yeah, exactly. Like and ask whether the question that you think you're answering is the one that you're actually answering.
Yep.
So that's why I like this question, because like on the face of it, you can say, oh yeah, the implementation level, or the or in some ways the algorithmic level, or the how, of the what, how, why. These are, that's totally like a description of what the brain is doing. But there's a much deeper version of this question. which is like, even if you can describe the biomechanics of the system, is that actually what the system is doing, or is this still just a level of description that doesn't like get at explanation? So if you guys are interested in the philosophy side of this, there's actually in our professional development series, we've got a philosopher who's going to be joining us. And she's going to talk about representations and meaning, and whether the things that we think that we're studying are actually the things that we are studying and the questions that we are answering. So that's pretty cool. What do you guys think?
Can I add something to that?
Yeah.
So one thing we should always keep in mind, that when we have a physical phenomenon, when we create a model of it, we translate it into some other symbolic representation. And there we have some rules to manipulate those symbols. Like we take a biological neuron, convert it into differential equations. Now, it doesn't mean that whatever we have now created as a set of differential equation is the neuron. Differential equations themselves have their own properties, which may have nothing to do with the biology of the neurons. So we should always know this, that when you are studying the model and when you are studying the phenomenon.
Yeah.
Often this gets very confusing, that there are a lot of papers out where you wonder, like, is this something relevant to the question, or is it just the behavior of the model? So always ask yourself, like, what are you studying? Are you studying the model? Because if you are studying the model, then most likely you'll be studying applied math. You should be there. If you are asking a question about the brain, then of course it makes sense.
Unless, of course, you're trying to create some sort of like intelligent artificial system, in which case studying the model might be the thing that you actually care about doing.
Absolutely.
Oh, all conversations end with AI.
Okay, here also I want to say something. Okay, this has been bugging me for a long time. I think we should also not assume that the singular goal of computational neuroscience is to build artificially intelligent agents. Or this is not the goal of neuroscience even.
Oh, big question. You saved the big one for the end.
No, but I mean, this is one of the goals. Like, this is not the only goal. I mean, we still have brains, and we would like to understand it. This is such a fascinating natural object. So even if it doesn't lead to development of artificially intelligent agents, even then, I think just for the sake of knowledge, it's such a great endeavor.
But hold on, not just for the sake of knowledge, public health. There's all these diseases that we need to understand the brain, to understand depression and Alzheimer's and Parkinson's disease, all these things. So
yeah, the clinically relevant one got only a few votes here, actually. But I think clinical relevant
brain disease.
Well, when we voted on the goals at the very beginning.
Oh, clinically
relevant got, normative actually got almost no votes. So sorry for people who actually care about that.
Yeah.
But the clinically relevant one was not super popular.
I think it's partly like selection bias. Like, you go to Cosine or one of these computational neuroscience meetings, and you think like the people there are like the rock stars of neuroscience, but you forget that like neuroscience is this big and computational neuroscience is like this big in terms of funding. Like, most of the money is going to like drug addiction, stroke, epilepsy, aging, Alzheimer's, PTSD, basically clinical studies.
But the overlap is definitely there too, right? Like, computational psychiatry is a growing area, and there's a lot of really interesting stuff happening there too.
Sean Escola, one of our board members, is one at a pioneer in that field.
I think that's actually a big point of what coming out of NMA you could potentially do, is you could take the computational tools that you're learning here and take them into some of these other realms that are less computational and massive, and have these big, potential health impacts or big kind of societal impacts. And there's a lot of value that computational neuroscience, which Jeff, as you so poignantly put it, is this big in the neuroscience field. But there's a lot of power here, and I think that paying attention to beyond just the basic science, which is also a laudable goal in and of itself, like, comprehension and understanding and basic science knowledge as a society. Yeah. But if you could take it and go into computational psychiatry or, computational neurodegenerative disease studies, those kinds of things, like, do it. And there's
brain development. I mean, brain development is really important for understanding things like autism and other developmental disorders, schizophrenia, and we definitely need more quantitative people working on those problems.
In fact, in development,
exactly. The point is that there are many avenues where you can take this knowledge of neuroscience, not just to make AI.
Yeah, exactly.
You can make AI, right? Like, I mean, you can if you want to study if you want to build an agent that learns how to learn, that does meta learning well, what better system to study than like a 2-year-old and how the 2-year-old's brain learns? Because
they're kind of slow though. Like every day you can barely see any progress.
Do you have a 2-year-old at home?
8 months.
Oh, okay.
Wow.
Yeah. Well, but they're not that slow. I mean,
I'm just joking. It's pretty amazing.
It is pretty amazing. Yeah.
Okay.
Yeah, computational psychiatry is something that I think is going to be growing also, and it's also something where it really is interesting because you actually learn a lot about a system when things start, quote unquote, breaking down, right? Like when things start becoming anormal, that's when you learn something about it. When your car suddenly has a weird sound coming from the engine, then that's when you actually start really figure something out about it, right? Like, so when things aren't working the way that quote unquote normally is, that's when you can really start learning something about the system.
Absolutely. Yeah. I mean, optical illusions are a great non-disease example of that, right?
Yep.
That's my favorite way to introduce some of this stuff is like visual illusions. It's like these two things are actually the same size, but your brain says they're not.
Yeah.
I like the checkerboard one.
Yeah.
The brightness, the shadow in the checkerboard. That's one of my favorites.
Yeah. My other favorite one, honestly, is the light from above prior, like where it looks like bumps and dimples.
Yep.
Because you expect light to come from the top, from above you.
Actually, the hollow face, right?
Yeah.
The hollow face one. That's so amazing. You
really?
don't even know when you're correcting for it.
Yeah, if anyone has ever been to Disneyland here, like in the Haunted Mansion, you walk by all those faces and they look like they're watching you. All the like carvings. No? Really?
No.
Oh man. Okay. Well, maybe some people who are watching this have been, but they make use of this illusion to freak you out in the Haunted Mansion as you're like going towards the little cars because they're all concave and so they look like they're turning to follow you, even though as convex things. Even though really it's just a concave, cutout. It's pretty cool. All right, guys. Well, thanks. Yeah, sending the links. Perfect. Okay.
Actually, there is a great link about optical illusions. Give me a minute.
Send it. This is a good place to end, I think.
I sent one link, but it's not that good.
So this one, I know Michael very well. He was an optician in Freiburg where I did my PhD, and he collected these illusions and explains them and breaks them. Right? There are these interactive graphics where you can break the illusion and see like where it's amazing what he has done for this.
What a great site.
Cool.
By the way, there's actually like an equivalent site at McGill for auditory illusions, where you like, depending on how close together information comes in the two ears, whether you hear it as two sounds or one sound. And it's like, it's pretty, I can't remember the guy's name. I could probably find it though. Auditory signals, exactly. I feel like somehow we're...
Ulrik, this is not your garage. This is your library.
Yeah, my
well, it used to be my garage, but nowadays then it's turned into my library.
That's the guy. What's his name again? Bergman?
Albert Bergman. Bregman.
Bregman.
Yeah.
Nice.
Yeah, I've actually been doing some of the modeling and that kind of stuff too. So that's why the book is, so close by.
Integration versus segregation. Yay.
Yeah.
That's so funny. I mentioned Gelman and there's two things and you're just like, oh yeah, I have the book here.
I do not have books like that handy. Not in my home office anyway, not right after I move.
Right.
Well,
my
guys.
office is pretty empty right now because everything's been moved into the garage instead. So, yeah.
Okay, that's a wrap.
I think that's a wrap, guys. We went even over a little bit. We were having so much fun. So I think we should let these guys go. They've got some hubs to go to, some little virtual rooms to go wander around and hang out. And the last thing I'll say is if you guys are still here and you're still listening, please go do your reflection surveys. Please, please, please. That's really a big deal. It helps you. It helps us. And that's it for today for the main events of Neuromatch Academy. And we'll see you back here tomorrow. Okay. Bye, guys.
Thank you.
All right, that's fun.